In section 3 of our first unit, we're going to begin to develop a library of different functions. We started the unit by looking at what functions are, how to find domain and range, and some different properties associated with them. So now we're looking at specific types of functions. So we're going to go through several different types today. These functions and their graphs are going to be used quite frequently through this course and in future math courses. Our book refers to them as the library functions, and I'm often going to refer to them also as parent functions. Okay? Understand that all of the functions that we put in our library, they all have what I like to refer to as critical points. Okay? And it's going to be crucial for you to learn the critical points associated with each type of function. Okay? Essentially, you want to have them memorized. All right? The first type of function in our library is known as the constant function. F of x is equal to some constant c that represents a real number. So as an example, f of x equals the constant of 3. Now, the critical points for this one really could be found with any x values, but I've just found, I've just set up a table here using the x values between -2 and 2. Right, now, the reason this is called the constant function is because it does not matter what value you evaluate for x with, the resulting y value is going to remain constant, in this case 3. So f of -2 would equal 3. F of -1 would equal 3. So would f of 0, f of 1, and f of 2. So let's plot all of those points. And you can see a pattern, right? Those 5 points are forming a horizontal line. And understand that those are 5 points out of an infinite number of points for this function. I can really plug in any value for x here. So a constant function will always graph to be a horizontal line. Now its domain will be all real numbers. In interval notation, that would be from -infinity to infinity. And the range is going to be whatever the constant number is, in this case, 3. Okay? All right, next function in our library is known as the identity function. F of x equals x. I'm going to use the same x values for my critical points. F of -2 would be -2. F of -1 is -1. F of 0, 0. And I think you get the idea. Go ahead and plot those. Okay, you have a line here. Okay. And I think you can see why it's called the identity function. Notice the input value of -2 results in the same output value of -2, so it's not changing identity, so to speak. Okay. Domain is all real numbers. I could have plugged any value in for x. And the range is also all real numbers. Okay. Moving forward, next in our library is the absolute value function. Its parent function is f of x equals the absolute value of x. Recall, absolute value is a number's distance from 0. Distance is positive, right? Distance implies positive, so all of our output values from this function need to be positive numbers. F of -2, the absolute value of -2 is 2. Absolute value of -1 is 1. Absolute value of 0. Absolute value of 1. And of 2. All right, when you plot those 5 points, you can see that a V pattern is formed. So absolute value functions will always graph to look like a V. Domain is all real numbers. That's because every number has a distance from 0 on the number line. And the range is all positive values, right? Y greater than or equal to 0. All right, moving on. Next we have the square or quadratic function, f of x equals x squared. Same x values for my critical points. If you were to square -2, that would result in +4. Squaring -1 would give you 1. Squaring 0 is 0. Squaring 1 is 1. Squaring 2 is 4. All right, now on some level this behaves similar to the absolute value function, but each half of the curve is not linear this time. Okay, instead we're going to get what we know to be a parabola, right? And pay attention to those critical points there. Okay, make sure you you have those down, and you know they're again essentially memorized, because we will start to transform these types of functions later on, and it's going to be helpful to know what those critical points are. Domain, all reals. Range, whenever you square a number, it results in either 0 or positive, right? All right. From the square, we can move on to the square root function. There's a typo here. Sorry about that. This is supposed to say square root. Let's fix that real quick. Okay. F of x equals the square root of x. All right, now we kind of already touched this a little bit in the last section regarding domain and range. This is going to be our first type of function in our library that doesn't have a domain of all real numbers. Okay, that's because you cannot take the square root of a negative value, right? Notice my critical points. The values that I've chosen for x are all perfect squares. That will ensure that my output values, my y values, are integers. Okay? Square root of 0 is 0. Square root of 1 is 1. Square root of 2 is, or square root of 4 is 2. Square root of 9, 3. Plot them. And we have to understand, again, that the x values cannot include the negatives, right? So that means that this point at the origin is an end point, and we can only move to the right. I like to describe that as a curved ray. Okay? Domain, x has to be greater than or equal to 0. And that's the same for the range, just y has to be greater than or equal to 0. Okay. Moving forward. From the square and square root functions, we can transition to the cubic function. F of x equals x cubed. And I have another typo in here. Let's fix that. I want that to be a 2. And I want that to be a 2. Okay. What does -2 cubed result in? That results in -8. -1 cubed is -1. 0 cubed, 0. 1 cubed. And 2 cubed. Plot them. Okay, some of you might be tempted to connect these with straight lines, but you actually get a nice smooth curve here. This is what your cubic function will look like. It has a domain of all real numbers, right? All numbers can be cubed. And it has a range of all real numbers. From there, we can transition to the cube root function. Oh, got another typo. Sorry. All right, so f of x equals the cube root of x. This time, notice my x values have changed. I'm using perfect cubes for my inputs. Okay, the cube root of -8 is -2. Cube root of -1 is -1. 0, 1, and 2, right? Plot them. And notice it's a very similar curve to the cubic function. Okay. Domain, all real numbers. Range, all real numbers. All right, moving forward, two more. Then we have the reciprocal function. Okay, this one we have very limited experience with. The most basic reciprocal function is f of x equals 1 over x. I think you'll understand why it's called the reciprocal function here in a minute after we complete the table. All right, now the values that you choose for x aren't nearly as important here. I kind of tried to spread them out a little bit so our points don't end up bunching too close together when we plot them. So f of -4 would result in -1/4. Okay, notice that y value is the reciprocal of the x value. That's why we're referring to this as the reciprocal function. F of -1 would be -1. F of -1/4 would be -4. F of 0, 1 divided by 0 is undefined. That's huge. That tells me 0 has to be excluded from the domain. F of 1/4 is 4. F of 1 is 1. F of 4 is 1/4. All right, plot all of those. You're just going to have to estimate their locations as best as you can. So -4, -1/4, -1, -1, -1/4, -4. 1/4, 4, 1, 1, 4, 1/4. All right, now, what you have to understand here is that there's actually two curves that are going to make up this one graph based on the behavior of these points, okay? So here's 1/2 of the curve. And the other half. And the reason we're separated like this is because of that fact that 0 could not be used in the domain, right? What we have going on here, we have the x-axis and the y-axis are both what are called asymptotes. The x and y axes are both called asymptotes. You might have heard that before from Algebra 2. Asymptotes are lines that your curve approaches but never actually touches. They get infinitely close, but they never actually touch. Okay? Based on that, we can say domain x cannot equal 0. That's negative infinity to 0, union 0 to infinity, and it would be the same for the range. Okay. All right, last type of function you saw in Algebra 2. We referred to it back then as the greatest integer function. Sometimes you'll hear it referred to as a floor function. And there's lots of different notations to represent the greatest integer function. So one such is simply int followed by x. The next looks like brackets, but they're missing the top of each bracket. That's my indication that it's a floor function. There is also something called the ceiling function, where you would have the top of the brackets and you'd miss the bottom of the brackets. Okay, and then sometimes you'll just see straight brackets used as well. Okay, nevertheless, no matter what notation here, what's in red is most important here. All of those notations mean the same thing. They mean to take the greatest integer less than or equal to x. The greatest integer less than or equal to x. So let me give you some examples. So we're working with the basic greatest integer function right here. F of 2.7. What's the greatest integer that's less than or equal to 2.7? Well, that would be the number 2. Okay. F of negative 3.4. Be careful with the negatives here. It might help to visualize this on a number line. Okay, negative 3.4, right about there. The greatest integer less than or equal to that would move you to the left on the number line to negative 4. And lastly, what's the greatest integer less than or equal to 14? Well, 14 is already an integer, so it equals itself. All right, now graphing the greatest integer function is unlike any other functions. Okay, we can still make a table of values, but notice that in my x column of the table, I'm not using a individual value for x. I have it set up to where I'm using intervals. Okay, so right here is an interval from -2 to -1. I've set that up that way because I know by this definition that's in red here, all of the numbers that fall between -2 and -1. So -1.5, -1.6, so on. All of those numbers should result in the same y value from this function. They're all going to result in a y value of -2. Okay. What is that? How does that respond or correspond to the graph? Well, the left value of that interval is -2, matching up with a y value of -2. That's going to lead me to this point that you see depicted on the graph. The other end of the interval is -1, and it matches up with -2. But do you notice how -1 has got a parenthesis on it? That means it's not actually included in the interval. So graphically, I represent that with this open point. Then I connect the two to represent all of the points whose x-coordinates are between -2 and -1 that have that same y value of -2. So that one interval just led me to an infinite amount of points that look like this, like one step of a staircase. Okay. All right, we move on to the next interval. Notice it picks up where the previous one left off. Okay. Any number between -1 and 0, the greatest integer less than or equal to it will be -1. That'll lead me to this point, and all of those in between. Next interval. Any number between 0 and 1 for this function will result in 0. That'll lead me to this point, and all those in between. And then the last interval, anything between 1 and 2 will result in 1. Okay. Now, sometimes students get hung up on why I started my first interval at -2. There was really no rhyme or reason to that. You can really start anywhere. Okay. Just make sure, try to fill up the graph. All right, domain for the greatest integer function is all real numbers. You can see that in the intervals that I've chosen. Okay. Where one interval stops, the next one picks up. Range, all integers. Look at your outputs. They're only integers.